Okay, thanks for the chairman. Good afternoon. I am Bo Li, a postdoctor in Wuhan University of Technology. I am on behalf of Professor Wei Chen to show the presentation. The topic of the presentation is carbonation resistance of slag blended cement paste modified by polyaluminum sulfate. The presentation is divided into these 5 parts. Firstly, we want to introduce some backgrounds of this work. This page shows what the polyaluminum sulfate is. As this page is showing, aluminum ions tend to polymerize and bonded together with hydroxyl ions at a certain pH to form polymerized ions groups containing multi-aluminum chlorides such as 2, 6, 7, 8, 13, and many other number of chlorides. Among them, a most stable species is polyaluminum ions groups containing 13 chlorides with a Kidding structure model like this. One tetrahydroaluminum ion in the middle, which is surrounded and bonded with 12 octahydroaluminum ions like this. The chemical formula of polyaluminum sulfate can be shown as this: 1 tetrahydroaluminum, 12 octahydroaluminum. Polyaluminum sulfate is recently developed inorganic agent for water treatment. The hydrolysis of PAS occurs in the water. Liquid aluminum NMR reverses that trimeric polymerized aluminum ions group with positive charge formed first in the water. Afterwards, the aluminum species transferred into monomers with negative charges. Delta potential test of slag modified with PAS, which had disappeared to water, shows that hydrolysis of PAS was observed in the surface of slag at very early ages and modified the surface charge of slag. Polyaluminum sulfate was named as PAS in our presentation. Our previous work shows that adding PAS with a dosage of 2% by mass improves the strength development of slag. After curing for 14, 28, and 56 days, MIP results of blended paste at 28 days shows that adding PAS reduces the porosity and densify the blended pastes. Based on our previous work, we proposed the research motivations. Adding PAS into the slag blended cement paste improves the hydration degree of slag, modify the microstructures, and improve the carbonation resistance of blended cement paste. In second part, we show the results of effect of PAS on the hydration of slag in the blended cements. We study the effect of PAS on the hydration degree of slag using silicon NMR tests. Silicon NMR tests of raw material blended paste after curing for 14, 28, 56, and 180 days were performed. After deconvolution, we calculated the average reaction degree of the slag particles at different ages. This figure shows that adding PAS with a dosage of 2% by mass improves the hydration degree of slag in the blended pastes at 14, 28, and 56 days. Reaction degree of slag modified by 2% PAS at 180 days was comparable with that without PAS. The exact pattern of hydrogen products shows that a hydroxide-like phase, potentite, and monosulfate were formed after curing for 28 days. Adding PAS increases the relative intensity of characteristic peaks of hydroxide-like phase. TG and DTG analysis quantitatively reveals the amount of hydrogen products formed in the past. The broad peak between 300 and 400 degrees was attributed to the weight loss of hydroxide-like phase. These two figures reveal that adding PAS increased the amount of hydroxide-like phase formed in the blended paste. This means adding PAS promotes the hydrogen of slag particles and releases more magnesium ions into the paste, facilitating the formation of hydroxide-like phase. This page shows the TEM image of hydrogen products after curing for 14 days. CAS gel shows a fine morphology which is enriched in the outer region. Some plate or lace-like nanocrystals were intermixed into the fine CAS gel in the outer region. More plate or lace-like nanocrystals were observed in the inner region of slag particles, which consists mostly of magnesium and aluminum elements. Lace-like nanocrystals seems to be hydroxide-like phase. As the hydrogen progressed, more nanocrystals were formed in the inner region. Nanocrystals were homogeneously distributed in the inner region of slag particles. This page shows the enlarged images of the plate or lace-like nanocrystals in the past. Here we show the lace-like nanocrystal in the outer region, and here we show some lace-like nanocrystals which are enriched in the inner region of the slag particles. Okay. The structure and the composition of the nanocrystals was analyzed with EDX and electron diffraction. Support EDX suggests a mean magnesium to aluminum ratio of 2.0. The electron diffraction of the plate or lace-like nanocrystal show obvious high-resolution lattice fringe and electron diffraction spots. This table shows the comparison between the calculated D values and that of standard hydroxide-like materials. The electron diffraction spots match well with the hydroxide-like phase, which was intercalated with hydroxyl ions and water molecule. This means the interlayer ions between two magnesium and aluminum plates were hydroxyl ions. Hydroxide-like phase formed in the blended paste modified by PAS were named as OH-LDHS. LDHS possess an ability to exchange interlayer ions with the environment. According to the thermodynamic stability, OH-LDHS can exchange the interlayer hydroxyl ions with carbonation ions in the environment to form CO3 LHS. Thus, OH-LHS formed in the slag blended paste modified by PAS presents a potential function to immobilize carbonation ions and improve the carbonation resistance. Then we show the results on effect of PAS on carbonation resistance of slag blended pastes. The carbonation experiment was performed according to Chinese standard. Blended pastes were cured for 28 days before carbonation. CO2 concentration was 20%. This is the image of carbonation depth test after carbonation for 28 days. This figure shows the effect of PAS on the combination depth of the paste after combination for 7, 14, and 28 days. Adding polyaluminum sulfate reduces the combination depth of the pastes. Three conclusions are drawn from our work. Firstly, adding polyaluminum sulfate improves the hydration degree of slag in the blended paste. Secondly, adding polyaluminum sulfate facilitates the formation of OH-LHS. Thirdly, adding polyaluminum sulfate improves the carbonation resistance of the slag blended cement pastes. Okay, that's all. Thanks for your attention.